Welcome to part 2 of the lecture on instruction scheduling. So, to recapitulate a little bit, instruction scheduling is nothing but reordering of instructions, so as to keep the pipelines of functional units full and make sure that there are no stalls. This is an NP complete problem, as are actually all good problems in computer science. So, we need heuristics in order to solve this problem, and each heuristic will have some efficacy, some may be better than the others, and we can apply heuristics on basic blocks, and that would become local instruction scheduling. And if we consider extended basic blocks called super blocks, then the scheduling strategy would be called as a global instruction scheduling strategy. So, what is basic block scheduling? We consider a model of basic blocks to consist of various micro operation sequences. These are the instructions that we have. Each MOS is indivisible. So, it is pipeline, but it is indivisible. Each MOS has several steps, and each of these sub steps will require resources, and we assume that each MOS sub step will require one cycle for execution. There are going to be constraints on the reordering process. So, some of them are precedence constraints and some of them are resource constraints. Precedence constraints arise because of data dependencies and execution delays, whereas the resource constraints arise because of the availability or unavailability of the shared resources. Quickly, a simple example to show the precedence and resource constraints. So, if u and v are related by an edge, and the delay on that edge is d, let us say sigma u is the schedule time of u and sigma v is the schedule time of v, then the delay must be less than or equal to sigma v minus sigma u. So, in other words, we cannot schedule sigma v d slots after sigma u, earlier than d slots after sigma u. Whereas, the resource constraints, let us assume that v 1, v 2, v 3, v 4 are scheduled in 0, 1, 2, 3 time slots. These are the sub steps of each MOS, and the matrix contains numbers which indicate the resource requirements of various sub steps. So, assume that we have 5 resources, and at I equal to 4, okay. So, that is we start here 3. So, this is 3, this is 4, right. So, look up the diagonal, and we have 2 plus 2 plus 1 as the resource requirements of all the instructions which are still active. See, this sigma v, the v 3 is active and v 2 is in its second sub step, and v 1 is in its third sub step, and v 1 has finished. So, we have to add up all these and make sure that it is less than or equal to 5, which is indeed true. So, the resource constraints are satisfied, but if you look at I equal to 2, then we sum up the resource requirements of all the 3 active instructions. V 3, V 2 and V 1 are all active. So, 3 plus 3 plus 2. So, that is 8, which is greater than 5. So, the resource constraint is not satisfied. That means, this particular schedule, the way we have put it here, is not a legal schedule. The simple list scheduling algorithm looks at a ready queue of nodes which are ready to be scheduled. So, to begin with, we have the root nodes of V, then we pick the highest priority node in the ready, then check whether it satisfies precedence constraints and find the lowest slot in which we can schedule it. We make sure that resource constraints are also satisfied and find a slot after LB during at which V can be scheduled. Then we update the ready queue and add this V to the schedule. So, this is the ready queue update. So, V is the node which is to be, which has been just now scheduled. So, it has many successors. 3 of these successors have predecessors which are already scheduled, which all the predecessors are scheduled. So, we can add the U1, U2, U3 to the ready queue, but X 2 has another predecessor X 1 that is not yet scheduled. So, X 2 cannot be added to the ready queue. The precedence constraints and resource constraints are quite straightforward. I already mentioned what they are. So, let us look at a picture. So, V is the node, and sigma u 1, sigma u 2, sigma u 3 are mentioned here as 10, 25 and 18. So, now what is the lower bound on sigma v, that is the slot in which it can be scheduled. Obviously, it will be the maximum of 10 plus 2, 25 plus 2 and 18 plus 3. So, that comes to 29. Okay. So, this is how the precedence constraint is satisfied, and the lower bound for sigma v is found. The resource constraint satisfaction, at any slot that we want to schedule, we must make sure that the resources are available. So, as I showed you in the a few minutes ago, scheduling V 3 here will cause a problem. There will be resource crunch. The same is true for this also. For example, if we schedule sigma we put sigma V 3 equal to 3. So, we would have 3 plus 1 plus 2. So, that is 6. So, again we are violating the constraint. So, whereas here it is 3 plus 1 4 and 1 plus 2 3 and this is 2. So, no problem, the resource requirements will be satisfied. That is the reason why 2 and 3 have been left free. Now, how do we pick the nodes from the ready queue? So, there is a priority ordering for nodes. One of the priorities that we use is the longest path from the node to a terminal node. So, that is something I can show here. So, you compute the path length starting from the bottom and travel to the top by adding the delays along the paths. And you also have E start and L start, the early start and late start deadlines for the nodes. So, let me show you a very simple picture of how it can be computed. U 1, U 2, U 3 are the 3 nodes which are already scheduled, the predecessors rather, and V is the node for which we want to compute the E start. U 1, U 2, U 3 have their E start already computed, not scheduled. So, 25, 45 and 16 are the E start times for U 1, U 2, U 3. The delays are 4, 7 and 2 on these arcs. So, again just like resource the precedence constraint problem, we compute 25 plus 4, 45 plus 7 and 16 plus 2, find that 52 is the max of all this, and that would be the earliest start time for this particular node V. So, that makes sense, it is just like satisfying the precedence constraint. And for the latest start, we consider from the bottom the nodes W 1, W 2, W 3 which are successors of V 12, 36 and 21. Subtract the delays and see which of these is minimum, and that is the time, the latest time at which we can start V. For example, this is minimum is 10, that corresponds to W 1 which is 12 minus 2 10. That means, if we schedule V at 10, then after 2 slots W 1 can be scheduled. If we schedule V earlier than that, then there is a precedence violation, and if we so therefore, we will require a pipeline stall. If we schedule V later than that, W 1 will have to wait for a slot. Okay. So, because W 1 will be ready at 12, if we schedule this say at 12, then W 1 will have to wait for 2 cycles, that is still 14 in order to get scheduled. So, either too early or too late will harm. So, our heuristic will always make sure that the slack, which is L start minus E start, is used as when it is used as the priority, we make sure that the lower slack nodes are given higher priority, and it so happens on critical path possibly the slack would be 0 and they get the maximum priority. So, let us see how these E start and L start values are computed for a non trivial example. We assume that add, sub and store take 1 cycle each, load takes 2 cycles and multiply takes 3 cycles. So, path length is written on the left hand side of the parenthesis, and the slack is written on the right hand side of the parenthesis. So, what is inside parenthesis are the E start and L start numbers. So, if you look at it closely, we start the E start computation from the top. So, the E start number is 0 for I 1, and then as I told you in the last lecture, we compute the E start values for I 3 and I 4 by adding the delay of load. So, 0 plus 2 becomes 2 and 2 on this side as well. Here also, because this is a root node, we start the E start value with 0, and from I 3 along the arc from I 3 to I 7, we have a delay of 1. So, the value of E start along this arc would be 2 plus 1 3, whereas, if we consider this path, the mult instruction will get 2 plus 1 3 and the add instruction will get 3 plus 3 6, because mult has a delay of 3. So, 6 is the max value and therefore, this gets 6. So, similarly, E start value of all the nodes are computed, and when we reach here, this is 7, there is an output dependence from I 8 to I 9. So, this is forced to become 8, which is 7 plus 1. So, we start the L start values from here. It is assigned L start equal to E start is the value assigned. So, we get a value of 8 for I 9. Now, the predecessors are considered. This has many predecessors. So, add has exactly one successor. So, when we consider add, we get 8 minus 1, which is the delay of this, as 7 for L start. Whereas, for this node, this is the only successor. So, again this gets 8 minus 1 as 7, and then add gets 7 minus 1 as 6, and then we go on. This add gets 6 minus 1 5, and this multiply gets 6 minus 3 as 3, this gets 3 minus 2 as 1, 3 minus 1 as 2, and from here this is 5 minus 2, that is 3, and this is 2 minus 2, that is 0, minimum is 0. So, this gets its L start value as 0, and from here we have two successors, one is here and another is here. So, we need to consider these two, and then this has 3. So, 3 minus 2 is 1. So, that is the minimum value. Of course, when you look at this arc also, you get 8 minus 2 as 6, but 6 is much larger than 0. This is the way the L start values are computed from the bottom towards the top. So, here is the program, and we want to schedule this particular program by reordering the instructions. So, we have so far computed the path length and E start, L start values. So, L start minus E start gives you the slack, and they are all noted here. So, let us try scheduling these instructions. As we said, add, sub, store require 1 cycle, load requires 2 cycles, and multiply requires 3 cycles. Let us assume that there are 2 integer units and 1 multiplication unit, and all the 3 units are capable of load and store operations as well. We can use the heuristic of either the height of the node or slack, and the schedule will be identical. So, let us look at slack, because we have already done one example with height of the node. So, to begin with, these are the 2 nodes which are in the ready queue, because both of them are the roots of the DAG. Okay. So, in cycle number 0, all the resources become just before the cycle number 0, beginning of it, all the resources are available. There are 2 instructions which need to be scheduled, both are load operations. So, load and load. We can schedule both of them on the 2 integer units which are available, and the multiply unit is not used. So, here 1 indicates that the integer unit is being used, and 0 indicates that unit is not being used. So, 1 1 0 indicates integer unit 1 and 2 are being used, but the multiply unit is not being used. So, 2 instructions are scheduled, both are load. Now, we cannot schedule any instruction in this particular cycle number 1 for the simple reason that load requires 2 cycles to complete, and before the load is complete neither of these 2 instructions nor this particular instruction can be enabled. So, we just keep cycle number 1 vacant, and during this period also int 1 and int 2 are busy, mult is 0 because load requires 2 cycles to complete. In cycle number 2, now we have all 3 of them enabled, right. So, this I 3, then I 4 and I 5, all the 3 instructions are now ready to be executed, the load has completed, but obviously we cannot schedule all 3 of them. There is a shortage of the units. So, even though there are 3 instructions, we cannot really schedule all 3 of them. So, we need to pick one or more of these instructions and schedule them. How to pick? That choice is made actually based on the slack. The slacks are 3, 0 and 5. So, it is obvious that the highest slack corresponds to instruction I 5, right. So, then we need to actually look at the lowest slack, not the highest slack. The lowest slack instruction corresponds to this I 4. So, I 4 is scheduled first. We still have another integer unit available, therefore, the next lowest slack corresponds to I 3. So, I 3 can be scheduled, but I 5 cannot be scheduled because there is no other integer unit available to us. So, we keep I 5 in the ready queue. Now, once I 4 completes, I 6 is enabled and it can be added to the ready queue. But remember, we cannot add I 7 to the ready queue because even though I 5 has completed, I 6 has not yet completed. So, in the ready queue we now have I 6 and I 5, one of them requires mult and the other one requires add. So, obviously, int and mult are available at this point, both are free. So, we take their services and schedule both instructions in the mult and add units. Now, the next step, we obviously cannot schedule in I 6 and I 5 etcetera in cycle number 2 because of shortage of units. Okay. I 5 is not scheduled in, there is no int available, and I 6 cannot be scheduled until we have completed an instruction. So, until I 4 completes we cannot schedule I 6. Okay. So, that is the major difficulty here, and we are using slack. So, we cannot go to I 6 even though it is a multiply unit and it is free, we cannot schedule I 6 ahead of another instruction I 5 because its slack is this is 0 and that is 5. So, we need to take care of these slacks also. So, we cannot violate the rules of the slack. So, what happens is we end up scheduling I 6 first because it has lower slack and then I 5 in this order. Okay. So, 2 cannot take anything because there are no units available. Now, the next one to be scheduled will only be instruction I 7. We are going to wait for a long time because multiply has not completed. So, please look at the picture again. This instruction, even though I 5 has completed and this is the next instruction, this cannot be executed until I 8 is completed. Okay. So, that is the major problem. So, we cannot execute this. So, we have to complete I 6, that means we require 3 cycles. So, we wait and then schedule I 7. So, I 7 is completed, then only one integer unit, I 8 is in the next cycle and I 9 is in the last cycle. So, this is how we actually schedule the instructions according to their slack, and that is about it. So, this is the example for scheduling with slack. Then we still have not formally considered how to represent the resource availability. I showed you an example here. This is the resource reservation table. that we are going to talk about very soon. It shows all the resources and their availability in the various cycles. So, we are going to have a reservation table, a resource reservation table for each instruction. Okay. So, for I1, a class of instructions, rather, each class of instructions will have a resource reservation table. This shows for the various time steps needed to execute any instruction in that particular class, what are the various resources used in the various cycles. So, for the two instructions I1 and I2, we have shown the two reservation tables. So, for example, R0 is used in cycle 0, but not anymore. R1 is used in cycles 1 and 2, and R2 is used in cycle 3. Similarly, R1, R2, R3 is used in the cycle 1, cycle 2 and cycle 3 and 2 and 3. So, from this we construct the global reservation table, which I have already shown you. There are time slots here and resources here, and it shows availability of various resources in the various time slots. So, the global reservation table is constructed as the schedule is built, which I have shown you just now. All the entries of GRT are initialized to 0, and GRT maintains the state of all the resources in the machine. GRTs can answer questions of the type, can an instruction of class I be scheduled in the current cycle, say Tk. So, this answer is obtained very simply by ANDing the reservation table of I with the GRT starting from row Tk. So, if the resulting table contains only zeros, then obviously resource is available, but if it contains ones along that particular column for that resource, then it is not available. Then the GRT is updated after scheduling the instruction with a similar OR operation. So, the AND operation is done in order to make sure that availability is checked, and the OR operation is actually going to be the one which updates the GRT. Then what we have seen so far is one method of scheduling called cycle by cycle scheduling. In other words, what we do is we look at the cycle and see how many instructions can be scheduled in that particular cycle and go ahead. So, it is not as if we pick an instruction and see where that particular instruction fits in the sequence of time slots available to us. So, obviously, this second method which I just now mentioned is also one of the scheduling methodologies, and that is called operation scheduling. So, list scheduling discussed so far schedules instructions on a cycle by cycle basis. Operation scheduling attempts to schedule instructions one after another. You just pick the instructions which have been ordered and schedule them one after another. It tries to find the first cycle at which each instruction can be scheduled. So, it is not the cycle which is picked and then the instructions which can be scheduled there, but we pick an instruction and see in which cycle it can be scheduled. Obviously, we need to make sure that precedence and resource constraints are satisfied for that particular instruction in that cycle. After choosing an operation I of highest priority, we make an attempt to schedule that instruction in the slack period, that is between E start and L start, and make sure that there are no resource conflicts in when we schedule that particular instruction in this slack period. So, what may happen? This scheduling may not be at the E start value, right. So, we may schedule an instruction at E start plus 1 or E start plus 2 etcetera, just before L start, at L start, or even after L start. Once if we have scheduled it exactly at E start, then the E start and L start values of the other instructions remain as they are. Whereas, if we schedule it in any slot other than E start, then the E start and L start values of the successors, the other unscheduled instructions etcetera, will definitely change. For E start the successor values will change, for L start the predecessor values will change. So, we may have to compute the E start and L start of the unscheduled instructions again, and then compute the slack as the priority for these instructions and continue with the scheduling of the instruction. Suppose no time slot can be found for an instruction I, then that is we do not find any slot between E start and L start for several reasons. It is possible that there are resource conflicts during these slots, or it is also possible that there are other instructions sitting in the time slots and therefore, the resources are not available. If this happens, an already scheduled instruction may have to be thrown out. So, that is we call this as descheduling of instructions. Which instruction? The one which is using the resources that we want for our instruction is descheduled, it is removed, and the instruction I is placed in this slot. The instruction J is again put back into the ready list and ordered according to its slack priority. Now, this may lead to a problem. I may actually place an instruction and then when you pick another instruction, my instruction may go out. So, this and then next time I kick the instruction which kicked me. So, we want to make sure that this does not get into a loop, right. So, to make sure that the algorithm does not get into an infinite loop, a group of instructions mutually descheduling each other, we place a threshold on the number of descheduled instructions. So, let us say we do not worry about the particular instruction, but just the number of instructions which have been descheduled. If this crosses a threshold value, then the L start value of the sync node is increased by 1, then we throw the partial schedule out, increase the L start value by 1, recompute the L start values and again restart the process. So, let us consider operation scheduling on the same example. So, this is the example that we have with 2 integer units, 1 the multiplication unit, all capable of load and store as well. So, here again we do not have a ready queue in the way we had it before. We are just going to keep all the instructions ordered according to their priority, and that is our ready queue. So, instructions sorted on slack with E start and L start values. So, slack 0 we have I 1, I 4, I 6, I 7, I 8, I 9. So, these are ordered according to the E start value 0, 2, 3, 6, 7, 8. Slack 1 there is only one instruction I 2 with E start and L start at 0 and 1. Slack 3 is I 3 with 2 comma 5 and slack 5 is I 5 with 2 comma 7. So, this is our sequence of instructions. We are simply going to pick the instructions one by one, see whether we can place it. So, for example, pick I 1, it should be put in slot 0 as far as possible. All the resources are obviously available, put it here. Next, I have this is the final schedule that is shown, not the partial one. So, I 2 is not yet placed. Okay. So, I 1 has been placed in slot 0. Next is I 4, place it in slot 2. So, how are we sure that the precedence requirements are taken care of? That is taken care of by the E start computation. So, we are not going to place any instruction prior to its E start value. Okay. That is why precedence constraints are automatically satisfied. We need to check the resource constraints. In slot number 2, I 4 can be indeed placed because the resources that is the int unit is available. Then comes I 6 in slot 3, which is fine, no problem. So, what is instruction I 6? I 6 is a multi instruction. Then comes I 7 in slot 6. So, that is again no problem, resources are available. Then I 8 in slot 7, I 9 in slot 8, and then we have I 2 in slot 0, that is possible because we have used only one integer unit in slot 0, the other one is still available to us. I 3 in slot 2, the same story, another integer unit is still available. So, we can use it, and I 5 in slot 2. So, I 6 is a mult, whereas I 5 is an add. So, integer unit is definitely available. So, we can place it in slot 3. So far we did not face any problem because there were enough resources in these slots available. But if you did not have two integer units, for example, we could not have placed both the instructions here. Okay. I 2 would not have been scheduled here, I 2 possibly, I 2 for example has 0 and 1 as its E start and L start. So, we would have actually placed it here without violation of any other precedence and so on and so forth, because if there is only one integer unit, I 2 will have to be placed here. The problem is more severe because I 3 for example, it has 2 comma 5, it cannot be placed here, and we would have placed actually I 3 in slot number 4. Okay. So, I 5 would have slot number 3, I 5 comes later. So, we would have placed this in slot number 3, and I 5 automatically would have been pushed to slot number 4. So, I 5 can be between 2 and 7. So, it could have been placed here. So, that would have got you a schedule using operation scheduling, but we would not have placed it at the exact E start value, because but there is a slack. So, there would not have been any pipeline stalls either. So, the length of the schedule would have remained as 9 as in this particular case. So, that is an example to show how operation scheduling can be done for basic blocks using slack as the priority. What are the problems with this simple list scheduling, either the cycle by cycle method or the operation scheduling method? The checking of resource constraints is a bit inefficient. Why? It involves repeated ANDing and ORing of bit matrices for many instructions in each scheduling step. So, there are many matrices here, and if there are many resources as well, the overhead may become considerable, but it is still not too bad, but there is a lot of work. How do we avoid such overheads? So, in other words, we want to actually get rid of the overheads involved in resource constraint checking. How do we do that? See, that can be done by constructing what is known as a collision automaton. Okay. So, what is a collision automaton? So, collision automaton indicates whether it is legal to issue an instruction in a particular cycle. So, that is what a collision automaton is all about. That is, let me show you an example. Here is the collision automaton for a simple example. These are the various states of the collision automaton. Each one of these states would have a matrix, and there are many edges going out of this particular each state. So, this is a finite state automaton. So, each of these edges is labeled with an instruction class, and so let us go back. So, the collision automaton, what does it do? It actually recognizes a legal instruction sequence. So, in other words, if we pick instructions from the ready queue, see if it is legal to be issued from a particular state, issue it, go to the next state, again issue whatever is possible, and so on and so forth. We actually get a sequence of instructions which is legal. Okay. So, because in every state we make sure that there are no resource constraints, and the precedence constraint part is taken care of by the ready queue. It avoids extensive searching that is needed in list scheduling, and it uses the same topological ordering ready queue as in list scheduling to handle precedence constraints. The most important part is the automaton can be constructed offline using the resource reservation tables. What are these tables? For example, it uses a collision matrix for each state. So, I showed you a collision matrix. For example, this is the collision matrix for I class, this is the collision matrix for F class, and this is the collision matrix for the load store class. And here is the resource usage vector for the instruction I class, that is integer class. The pipeline requires the integer decode in cycle 0 and nothing in cycle 1. For the floating point, it requires the floating point decode and nothing in the next one. For the load store, it requires integer decode, then the memory, and again it requires memory in the next cycle as well. Okay. So, this is the resource requirement, not that this is a great pipeline machine, but it is it suffices to show our example. So, this is the reservation table showing for each instruction class what are the various resources used in the various cycles, and in the collision matrix, for example, the size of the collision matrix is number of instructions into the length of the longest pipeline. So, say here for example, this is the length of the pipeline, that is 2. So, we have as many rows as the number of instruction classes and as many columns as the length of the pipeline itself, longest pipeline. What does a 1 or 0 indicate in this collision matrix table? So, for example, it says for the instruction class I in cycle 0, if we issue another instruction of I class, okay, this is the table for I class. So, all these are I class considerations. Okay. So, this says whether it is legal to issue another I class instruction in cycle 0 or cycle 1, and in cycle 0 if we issue that another I instruction, one is already in progress, we are trying to issue another one, there will be a conflict. That is what this one indicates. How did this happen? It is simple. Each I class instruction requires the ID unit. So, we cannot issue 2 I class instructions in cycle 0, there would be a conflict of interest. Whereas, if I issue the first I class instruction in cycle 0 and the second I class instruction in cycle 1, there is no conflict, because cycle 1 does not require ID again. There is obviously no conflict between I class and F class instructions. So, both cycle 0 and cycle 1 have zeros here. So, it is legal to actually issue an F class instruction along with an I class instruction either in cycle 0 or in cycle 1 after the I class instruction is initiated. There is a problem with the LS also, because LS also requires ID unit in cycle 0. So, we cannot issue an I class and LS class instruction together. So, there is a conflict in cycle 0, but in cycle 1 LS requires only mem. So, there is no conflict. Let us look at the F. No conflict between I class. So, both are 0. Conflict in cycle 0 of F class. So, 1 is here and a 0 is here, that is what this is, and there is no conflict with LS. So, because LS does not require the FD. How about the last one, LS class? There is a conflict with I class, I cannot issue LS and I in the same cycle. So, this is 1 and this is 0. I can issue F with LS, no problem, because it does not require any ID unit. I cannot issue another LS instruction together with this LS instruction in either cycle 0 or cycle 1. So, both require mem. So, there will be a conflict. That is what this is saying. Sij equal to 1 if and only if ith instruction class creates a conflict with the current pipeline state S if issued j cycles after the machine enters the current state S. So, that is why there are many states. Now, so once this is sorry, I read the wrong statement. This is the collision matrix for each state, but in each instruction class I also has a similar collision matrix. So, I ij equal to 1 if and only if instruction class I would create a conflict with instruction class I in cycle j if launched in the current cycle. Okay. So, that is what I showed here. These are the instruction class collision matrices. These collision matrices are created using the resource vectors. Now, we also saw the matrix in each of these states. What is that about? That is what this is. So, in the collision matrix for the state Sij equal to 1 if and only if the ith instruction class creates a conflict with the current pipeline state S if issued j cycles after the machine enters the current state S. So, in other words, the first column corresponds to the current cycle, the next column corresponds to the cycle after the current cycle. So, current cycle plus 1, and if we had a third column, it would have been current cycle plus 2 and so on. How many columns do we have? That is straightforward, as much as the length of the pipeline, longest pipeline. So, that is what we have 2 here, and how many rows do we have? As many as the number of instruction classes. So, that is 3 here. And how does the whole thing work? To begin with, we are in state 0. Okay. So, forget the blue color for the present. The collision matrix has all zeros because all resources are available, no instructions have been issued so far. So, there are no conflicts. Therefore, it is legal to issue any instruction from the state F 0, the start state. So, let us say we issue either I or F or LS. We go to a different state. How do we compute the new state here? Just take this particular state collision matrix, OR it with the collision matrix of that particular instruction class which you are considering. So, when we branch on I class, okay, take the I class collision matrix which is 1 0 0 0 1 0, OR it with this. So, we get 1 0 0 0 1 0. Similarly, if we issue an F instruction, we get this ORed with the collision matrix of the F class which is 0 0 1 0 0 0. Then for the LS we get 1 0 0 0 1 1. Now, the situation becomes slightly more difficult. Which instructions are legal from these 3 states? So, to check that, what we really do is, we have we have launched an instruction, but we have not advanced any cycle counters. We are still in the same cycle as we were in this particular state. Let us say we consider state F 1. Look at the first column which corresponds to the current cycle. If there are any zeros in the first column, then the instruction corresponding to that particular row or the instructions in the class corresponding to that particular row are all legal to be issued from this particular state without any collision. So, in this case the F class instructions are legal to be issued from the state F 1, but there is a 1 in the other 2 elements of this particular vector in the column I class and LS class. So, those are illegal to be issued from the state F 1. Why? That is straightforward. There are already ones here. So, in the same cycle I cannot issue another I class or LS class, whereas F class is legal. So, it is legal to issue another F class instruction from state F 1. Let us do that. What do we get? The new state that we get obviously is not this. We take 1 0 0 0 1 0, OR it with this particular F class collision matrix. So, there is a 1 here and that comes here. So, we get 1 1 1 0 0 0. Now, there are no more zeros in the first column of the state F 1 prime that we just now computed. That means, we have only 3 classes of instructions in our example. That means, there are no instructions belonging to any class that can be issued legally from this particular state F 1 prime, because it has all ones in the first column. There would only be collisions if we issue them. In such a case, what we do is we have to now advance the cycle by 1. How do we capture that effect in the state diagram? Simply left shift. So, we now have f 1 prime has 1 1 1 0 0 0, simply left shift by one column the new state matrix that we got. So, if we do that, this 1 1 1 0 0 0 becomes 0 0 0 0 0 0, because 0 shift from the right hand. That state is nothing but the start state. This indicates that now again all the resources are available. If we had any ones here, 0 1 0 or something like that in the second column, then 0 1 0 would have become the first column. We would have gone to a new state, not this particular state. So, from here on issue of f, we go back to this particular state f 0, and we have also advanced the cycle. So, that is precisely what we want to show here. This blue indicates that it is a cycle advancing state. So, once we jump to that state, we find that it is a cycle advancing state after the left shift of the column. We jump to f 0 and then advance the cycle. So, let us look at this state f 2. Again, this has only one in the first column. So, it is legal to issue I and ls class instructions from f 2. So, there are two arcs, with one with I, another with ls. With I, if you OR it with the I class collision matrix, we get all ones in the first column. So, similar to f 1, we left shift and then go back to f 0. Whereas, if we had issued an ls class instruction, that was a 1 0 1, and there was a 1 in the second column also. So, this matrix becomes 1 1 1 0 0 1, and when we left shift it, it becomes 0 0 1 and 0 0 0, that is what we have shown here. So, again we come to this new state, and that is a cycle advancing state, because we have done a left shift. So, from here again we find that there are two zeros. So, I class and ls f class are legal to be issued. So, we issue that, okay, I and f. So, we go to this particular state on I and f on this particular state. Again from here, when we issue an I, we go to this state and so on and so forth. This is how the collision automaton works. How do we use it in scheduling? So, let us see. So, I hope this is understood. The salient points are, when we have a start state, all resources are available. So, any instruction can be issued from the start state. Once we issue an instruction, to compute the new collision matrix, we OR the state matrix with the collision matrix of that particular instruction class, we get a new state. We check the first column of that particular state to see if it has any zeros. If it has, then the column, the instructions corresponding to that class are legal to be issued. If there are only ones, then we left shift the matrix by one column, and then if it is a new state, we go to that new state and make it cycle advancing. So, that is the summary of the state collision automaton and its construction, working, etc. So, what are the transitions in the collision automaton? So, whatever I said is formally written here. Given a state S and any instruction I from an instruction class I, S of I comma 1 is equal to 0 implies that it is legal to issue an instruction I from S, that is what I said. Only legal issues have edges in the automaton. The collision matrix of the target state S prime is produced by ORing the collision matrices of S and I. When no instruction is legal to be issued from S, S is said to be cycle advancing. In any state, this is important, a no op instruction can be issued. It is always legal to issue a no op instruction from any of these. We have not written the collision matrix for NOP class, but there are going to be no collisions with any NOP instruction, because NOP does not require any resources. Such a state behaves as a cycle advancing state only when a no op is issued. Otherwise, it is not going to behave as a cycle advancing state. What is a cycle advancing state? collision matrix is produced by left shifting by one column, the collision matrix appears. So, such a state represents the start of a new clock tick in all pipeline. In single instruction issue processors, all states are cycle advancing. Start state is of course cycle advancing, and states in which NOP is issued behave like a cycle advancing state. So, now how do we do instruction scheduling with the collision automaton? Fairly straightforward. You begin at the start state of the automaton. Remember, we have the same ready list that was available to us in cycle by cycle scheduling. So, pick instructions one by one in the priority order from the ready list. So, if it is legal to issue the picked instruction in the current state, that is you have a 0 corresponding to that instruction class in the state matrix, issue it. There is no advancement of the cycle counter now, but there is a change of state on that particular instruction class. Take that arc, go to the new state, compute the collision matrix by ORing the state matrix with the collision matrix of the instruction class. Now, you must update the ready list, because once this instruction is issued, its successors become eligible to be issued, and repeat the steps 2, 3, 4, right. So, this goes on, but if no instructions in the ready list are legal to be issued in a state, then we insert a no op in the output and compute the collision matrix as we explained for the cycle advancing state, that is left shifting of the column. Now, we also advance the cycle counter. Why? And go back to step 2. The reason is there are no instructions which are legal to be issued. Now, we insert a no op in the output, that means a no op will be executed when nothing is being possible, no new instruction it can be executed. So, once we do that we have actually skipped one cycle, right. So, that means it is a cycle advancing state. Now, because we have skipped one cycle, it is possible that more resources are now available. So, that is why the left shifting of the column takes place. So, once we do that, more resources may be available once the cycle has been skipped, new instructions may be schedulable in the current cycle that we get. If step 5 is executed repeatedly, the start state will be reached at some point, and in the start state obviously all the resources will be available. Why? Look at it this way, each one of the instructions requires a finite amount of resource, and it will definitely complete in a certain finite amount of time. So, if we go on skipping cycles and insert no ops when all the resources are busy, eventually in a couple of cycles all the resources will become available again. In other words, if we execute step 5 of cycle advancing state repeatedly, in a few steps after all the resources become available, we will be reaching the start state. So, again we can start reissuing instructions from the start state onwards. So, this is how the collision automaton works. The advantage of the collision automaton is that we do not have to do any checking of the resources using reservation tables etc. That is all inbuilt in the collision automaton itself. But the problem with collision automaton is its size can become very large for a very large instruction set. So, people actually have looked at this issue. They have considered factoring the automata, making smaller automata and so on and so forth. So, these are some of the advanced topics that are outside the scope of this particular lecture. So, this is the end of the lecture today, and in the next lecture we will look at optimal integer linear programming based instruction scheduling. Thank you.